Well, good afternoon, everybody. My name is Wenming Yi. I'm a solutions architect at the Amazon AWS Web Services. And here I also have Miro Enough from Nvidia, who is also a solution architect. And Miro, you'd like to maybe introduce about some of the things that we've worked together?
Yeah, absolutely. So we've had the opportunity to collaborate on multiple projects, including numerous training sessions at Amazon, focusing on machine learning and deep learning. Yeah, and today we'll be talking about our latest collaboration focused around the unique challenge that the new biosphere buildings in Seattle are presenting to the horticulturalists who work there.
Yep.
So our agenda for today.
Yeah. So first of all, we'll do an introduction and we'll show you a video of the Amazon spheres. If you haven't been to our new building, I definitely would encourage you to stop by when you're visiting Seattle. It's one of the new attractions of Seattle. And then the second part we're going to go into is a new approach of which we are using the state-of-the-art deep learning methodologies to look at and analyze some of the more complex data streams that's coming from the sensors, hundreds of sensors of the building. And finally, we're actually going to look at the architectural design from the systems perspective. So there's really two architecture we're going to be talking about. One is the deep learning architecture, and the second is the actual systems architecture in the cloud. And finally, we would like to tell you a little bit more about the results, which was actually quite impressive. And since it's a very adaptive solution, it's able to filter out a tremendous amount of false positives. And finally, we'll talk more about the future work we're going to be doing, essentially involving a lot of multi-spectrum cameras to look at issues with some of the plants and the long-term effects of having plants in a glass dome that actually filters out a lot of the infrared.
That's right, that's right. Yeah. So why don't we start with a quick video here, and let's see if we can make this work. Let's try.
A living wall is a marriage between technology and horticulture. It's a way of growing plants that are adapted to an epiphytic lifestyle on a vertical surface. It's quite a visual impact when you're walking into the space. We're in an off-site facility that we are using to pre-grow all of the living wall panels that will be installed in the spheres installation. This is generally the size of the plant material that we're starting with, and it's as easy as stretching the material out and situating the plant there. We do have a really pretty impressive diversity, around 200 different species of plants, and we used about 25,000 individual plants to start. For the living wall, it's a way of really kind of packing in the biodiversity and just the overall photosynthesis that's happening in the space. I mean, it's fantastic.
All right, awesome. So actually, the level of biodiversity has only gone up since then. So now they're up to 700 unique species and a total of 40,000 plants over the.
And we're actually increasing on the number of plants. And they actually, what they're doing is, you saw the video earlier, we have an off-site greenhouse, which we actually rotate plants into the biospheres, and depending on the season, and also depends on the type of plants.
That's right.
That we have.
That's right.
Yeah.
Yeah. And so really, our motivation here is to help these guys, Ben and Claire, who have become our good friends, and they have to take care of all of these plants, and it's a real challenge for them because as Wenming was saying, we're looking at over 189 sensors that are instrumented, and there's probably more than 300 in the building. And these folks care about them deeply. They go around and do rounds in different little zones of the building where they're monitoring with their logbooks all of the different plant flora species. And I mean, they have poured their love and life into this. I think Ben has tried over I don't know how many different types of materials before he found one that works for the living wall.
If you look at the image on the right, these are actually the nylon materials that they use. So essentially, in a living wall, we spray water onto the wall, and the absorbent material actually is able to distribute them evenly throughout the wall so that the plants actually get even growth nutrition. So they're not going to be drawn, or they're not going to have any kind of. When we met Ben for the very first time, he was telling us about these stories, and it was super inspiring. He said he tried 400 different type of materials.
Don't give away your secrets. Yeah.
Yeah.
No, absolutely. It's a really impressive achievement what they've accomplished, and it seems to really bring a lot of joy to people, who enter the building. It almost puts you into the climate of Costa Rica, while outside it might be just crappy Seattle weather.
Especially when it's winter time. If you have a cough and I walk into the building, by the end of the day,
it's cleared up.
It clears up. So maybe we can start.
Yeah. So just to really quickly
talking about the sensors.
Just talk through some of the sensor streams that we're tapping into, and we're actually working with some folks who are doing industrial building maintenance and instrumentation, and they have provided us with a site survey tool that allows us to capture these sensor streams. And so here what you see is just a histogram of the different types of sensors that we have access to.
The number of, right?
Yeah, and the number within each category. So you notice temperature sensors, humidity sensors, light level sensors, electricity demand, dew point, accumulated light, and CO2. And so these are all different forms of sensing that are happening within the building. And as you can imagine, if you're one of these horticulturalists, it's really difficult to stay on top of all of these signals to figure out what it means. So typically, they kind of just ignore them altogether, and for this and for other reasons as well.
I think the main thing is about the false positives.
Yeah.
So if you have sensors that essentially keep sending you lots of messages, just like if I receive lots of emails about things that are not actionable.
Right.
I think the main thing is that you want to be able to receive signals which the caretakers can actually take action upon.
That's right. That's right.
So that's really the key.
That's right. Absolutely. And so just to give you guys a little bit of a sense of what these signals look like, here are some temperature sensors. The first plot on the top showing a single floor, and then the plot below showing a different floor, and then the plot at the very bottom combining them together. Here you see CO2, and you can see that they have very different characteristics.
Yeah.
And here is instantaneous light levels that are being captured by the building.
Yeah, just for the audiences that are curious, you want to talk about some of the spikes in the data in the background there?
Sure. So those spikes are triggered by multiple things. The building itself is trying to calibrate the total amount of light that's being consumed, and so it tries to integrate over these instantaneous light levels and figure out how much light is being carried into the building, both from our lighting system and from external things like the sun. And so whenever the cumulative amount of light for a particular day drops below the level that is required, the following day the building will controllably try to increase its light output to try to make up for that.
Yeah, so we essentially have a set of artificial lights that are controlled by these sensors.
Right, in addition to the ambient lighting that's
right.
coming into the building. That's right.
Especially, it's actually difficult to do just because there's cloud covers, there's amount of sunlight, and also seasonality. So we have a lot of, we have very little daylight in Seattle, probably about only 7 hours around this time of the year. So there's a lot of compensation you have to do.
That's right, that's right.
And we can talk more about complexity that goes even further because we don't have infrared lights.
That's right.
Yeah.
That's right. Yeah, and so
actually ultraviolet. I'm sorry, it's not.
Right.
Ultraviolet.
Yeah.
That's right.
So just to sort of recap, all of these sensor streams are coming in, and at this point, they're being orchestrated by this building management system, which allows you to sort of set various thresholds and set points if you wanted to build alerts for yourself for the different levels and activations of the sensors here. But as you can see, there's so many complex data streams that it's really difficult to come up with any kind of heuristic way of putting together some sensible boundaries or fences around logical behavior. You've got hundreds of sensors to manage. And in practice, what we end up seeing, and apologies for the small font here, but these are some suspicious values highlighted in purple over a timeline that are being generated by the existing system. And as you can see, one of the sensors has suspicious values for the entire duration of the day, and the other sensor has multiple spots of suspicious activity. And when you actually look at the data coming during this time, it turns out that one of these sensors was just improperly configured, and the other one I think was just being obscured by a leaf.
Yeah. Once again, there's 196 that we can actually have access to. Just imagine if one of them goes down every day and you try to investigate that. There's really a lot of work. It's almost like a full-time job building maintenance person. And humans generally, when they see these repetitive false positives that don't have a lot of actionable values, they tend to ignore them.
Oh, yeah.
So the relationship between the humans and the system kind of grows apart after you
lose trust.
Yeah, you actually lose trust of the system.
That's right.
So what our new approach does is actually gains trust with the caretaker.
Yeah,
and what we'll show you.
That's right.
Because it's adaptive.
That's right. That's right. So basically, as a result of the way that the system is currently orchestrated, it has lost the trust of the caretakers. And so these are a couple of examples of what you might consider, real instances that alerting should be happening, but they were essentially ignored just because, the caretakers have built up a resistance to these false positives. And so the first occurred when the Alexa microwave integration product launch occurred, and that was at a time when the building operators requested that they change the temperature conditions on the highest fourth level of the building so that the media who's coming in can be a little bit cooler. And also I think they changed the air velocity. So those were settings that were fine to change temporarily, but it turns out no one set them back to their original set points. And so that was a problem.
Yeah, what's interesting is that we actually found this through the data without actually knowing which day it was. What we did is actually we used our new method to look through the data set, and we found an anomaly, and then we talked to Ben, and then Ben basically told, yeah, that's right, I remember that. That was essentially September 20th when the Alexa product was being launched. New Alexa products were being launched.
That's right, that's right. And the other one was when I guess building automation staff were coming in to try to do new sensor integration, and they suspended the irrigation for the living wall, which apparently was not even a critical thing to do. They probably could have done their work without doing that. Right. But it turns out no one, again, remembered to turn the water back on, and so the plants basically went thirsty for 24 hours, which isn't the end of the world, but it's not a good thing either when you're trying to maintain all of these crazy species.
Exactly.
And so essentially our approach to this problem, now that we've sort of covered the challenges, is to try to bring best practices from modern AI to this.
That's right. So I would say, for our audience here, which is an architectural track, so I think a lot of folks are actually new to machine learning and deep learning. So our particular session is really aimed to help you understand what's coming next, which is how AI is going to change how IoT systems will operate, for one, and how you can actually save money and also build a really good relationship between the users of your product. It's really about the user experience.
Exactly.
But at the same time, we also need to look at the hardware and also how the software is being deployed. How do we train the model? How do we deploy the model? This is essentially what our session is really aimed to achieve. If you don't necessarily understand the deep learning, the details of deep learning, don't worry about it. We'll actually have other sessions which we will go into a lot more details of that.
That's right. That's right.
Yeah. So I think the first thing that I want to point out is that we talked about the losing trust with the traditional system, which are essentially threshold-based or rule-based. The new methodology of using deep learning, it's adaptive. The system is adaptive so that it cuts down the false alarm rate dramatically. Mm-hmm. So what ended up happening is that Ben and Claire when a signal is generated, they'll look into it and they go, hey, what is actually wrong? So they're actually more motivated to investigate.
They have their curiosity back.
That's right. The curiosity is really what's helping. And also, there's a lot of these systems can be real time and very low cost if you implement them correctly.
That's right. That's right. And we'll try to give you guys a little bit of perspective on that as well.
We can talk about how we balance the cost by moving the inference into some of it in the cloud, and maybe some of the inference could actually be in IoT edge devices, which you would actually be putting them inside the building. Mm-hmm. And finally, it's also about scalability. So we're talking about a few hundred sensors here. So there are, let's just say, imagine 5 years from now. So a lot of the buildings will have a lot more sensors,
right?
Probably thousands and thousands. Mm-hmm. So the deep learning architecture we are talking about here is very scalable, but we also want folks to understand what are the options that you can minimize the cost.
That's right. That's
Yep.
right. Okay, so with that, let's talk a little bit about
Deep learning?
Deep learning, yeah, and why we're choosing this approach. So for folks who haven't, looked at this before, it's just a high-level explanation that just is meant to say that artificial intelligence is sort of the broadest context, and it's meant to capture, human-level intelligence across multiple tasks and multiple domains. We're very far from that, I think we can all agree.
Yep.
Machine learning is just sort of the subdomain where we're trying to develop algorithms that can improve themselves and learn from data.
Yep.
And one of those types of algorithms within machine learning happens to be deep learning, which is the one that is inspired by neuroscience. Yeah, and that's the purple circle here. Yep. These are the different schools of thought or different machine learning tribes and how folks have thought about how to solve these problems. If we were to compare the existing method that sort of lives in the building automation system today, would fall probably under the symbolist branch, which is where rule-based systems and some of the earliest computer scientists, where they were building logic-based systems.
Yeah.
That's probably where this would fall under. And it's a fine approach if you spend all of your time just looking at these numbers and trying to use your brain as the adaptive mechanism by which you continually set new thresholds. But from the perspective of a human having to deal with this many sensor streams, that's more than a full-time job.
Exactly.
So we're not really going to step too much farther into these different various approaches, but just sort of for your interest, if you're curious about this farther, check out the Master Algorithm, which is a book by Pedro Domingos, which does a great job of covering and highlighting the pros and cons of all of these different ideas. And it's not to say that deep learning is the end-all, be-all solution to machine learning or AI. It just happens to be probably one of the best methods that we've seen up to date at absorbing learning at really high scales. So in this plot, essentially what you're seeing is that many of the traditional approaches, as the data set size increases on the x-axis, they learn and they learn, but they sort of get saturated after a while. And then with deep learning, it doesn't really make sense to start building these large neural network fabrics until you have a lot of data, but we don't have that problem. We have tons of data.
That's right, especially for IoT, where you generate tons and tons of data. So having more data is actually a good problem to have. Part of it is also that deep neural nets are able to capture much more complex models.
Exactly,
because some of the models that we built for machine vision have hundreds of millions of parameters, right? Instead of just a few parameters of the traditional methods.
And also, all of these parameters are sort of woven together.
Exactly.
Unlike something like maybe like a decision forest made up of decision trees, or a random forest, or a gradient boosting mechanism where the trees don't really talk to each other. And so
it's a network.
This is like a very powerful paradigm. We're just starting to understand why they work so well, but empirically we're observing that they do great. It doesn't hurt also that it's inside of our brains, and it's kind of like a proven proof point, right?
And one of the difficult part of deep learning that we're still doing a lot of research on is the fact it's not as interpretable. So for example, decision trees we talked about here, but which branch it's going through. We know how the machines actually make those decisions. That's why when the system detects a signal, that signal would have to be explained somehow by a human. It can be difficult by looking through the system. However, with the human experts, they would be able to explain it to you.
That's right. That's right. Yeah. So there are definitely pros and cons, but I think one of the advantages is the level of performance that you can get out of this, and that's kind of really what we're hoping to do. Both the level of performance, the ability to capture data at really large scales, and to sort of become adaptive, to sort of keep learning and relearning, and to sort of stay ahead of all of the system behaviors.
Yep.
So the specific type of neural network architecture we're going to be using for this problem of anomaly detection, or basically finding surprising things in the data, is known as an autoencoder. And it's just pictured here. And what you can see is that on the left-hand side is our input to this architecture. And in our context, an input here is going to be time series data coming from all of these sensor streams. So you can think of each one of these neurons as receiving a single timestamp of a particular sensor data point. And as you can see from this architecture, the data flows from the left to the right. And so the input comes in on the left, and it's sort of forcibly compressed into its narrowest stage, which is known as the bottleneck, where the data has to sort of become condensed and summarized. And from that representation, it gets, again, sort of decompressed through the decoding stage and gets reverted back to its original full dimensionality reconstruction. And the objective of this network during its learning is to allow all of this data to stream through that's being generated by the sensor streams, and to get really good at having to summarize and compress the data, but then reconstruct it. And so it's trying to minimize the difference between the input and its reconstructed output.
Yeah, I think part of it is also the fact that we want to show people who haven't seen a neural net before is that there is a lot of connectivities between the neurons,
Right.
and they all inference each other to capture that very complex, I would say, complex mathematical relationships between all the variables.
Absolutely.
And we'll see the examples right after. Maybe
That's right.
Okay.
Yep.
We'll go.
And so specifically to sort of make this problem presentable to the network, we have to take these time series data sets that are coming from various sensors and present them as fixed size inputs, because the network architecture is fixed once we decide on a particular input dimensionality.
Yeah, essentially that's the size of your input. So
That's right. That's what the network's looking at to determine whether or not there's something surprising.
That's right. And we were using a sliding window way, which we're moving. So the data frames that we have, the smallest unit of time is 15 minutes.
That's right.
So essentially, imagine it as a sliding window that moves from left to right at 15-minute intervals.
That's right.
And
That's right.
until it finishes sweeping the entire data set.
That's right.
So that's essentially the training.
That's right. So this is a single sensor, and in our models we use many sensors at the same time. But this same idea holds, is that you essentially want to slide this window around, moving one sample at a time, so it has high redundancy with its previous member. But you also generate a lot of training examples for the network to see. And so as you build this architecture and you present it with tons of these data elements, you are now entering a place where neural networks become happy because they have tons of things to look at.
But as you can see, there's a lot of computation that's going to be required in deep neural networks. There's a lot of neurons that are part of the network, and there's a lot of mathematical propagation and calculation that has to happen throughout that complex network.
That's right. Yeah. So tons of opportunities. But so just to sort of close the loop on preparing the data so that it can be ingested by these models, we have to do all kinds of fun things like data wrangling to make sure that we account for missing data, make sure that everything is re-indexed so that all of the time sensors are being presented to the architecture with 15-minute sampling rate, even though they may not actually have that as their inherent sampling rate. We have to do normalization within the sensor types. And then another interesting thing that we discovered was that if you look at this cross-correlational matrix, which is, I realize, probably a lot to take in from a single slide, but just sort of look at the sort of shapes that you see. Each one of these dots in these matrices is representative of the strength of the relationship between two pairs of sensors. So, for example, the first row represents the strength of the correlation between the CO2, the first CO2 sensor, and all the other sensors that we're presenting in this sample. And so here you can see that CO2 is highly correlated with other CO2 sensors. It's highly correlated with temperature and dew point, and a little bit with instantaneous light sensors, and also the hourly index. And interestingly, it turns out that the behavior of correlation, or sort of the relationships that we see between these sensors, is different in the weekdays than in the weekends. And primarily that seems to be because in the weekdays there's a lot more people present. A lot more folks from Amazon are coming in to take a break and meet their friends. And so the CO2 activity actually ends up being much more correlated with other parts of the activity graph. And so for this reason, we decided to focus our first sort of model building research just on weekdays.
And also on the weekends it's actually closed. So
they're open on every third Saturday to the public.
Yeah, that's
or
right.
something.
It opens once a month to the public.
Right.
And of course you can find an Amazon employee that can take you to the spheres during the day.
That's right.
Any day during the week. Yeah.
But I think from the perspective of the caretakers too, the daily activity is probably the thing where most of the anomalies are likely to happen anyway.
And the other thing is that Ben has talked to us about is that on the weekends, if a sensor creates an alarm, he actually has to go in.
That's true.
And fix it.
That's right.
Yeah.
So we'll also build models for the weekend. That shouldn't be a problem. Okay, so this is just another sort of way to visualize and think about this data. So again, just to recap, we're chopping up all of these pieces of data coming through the sensor streams and presenting them to the network in the sliding window format. And what the network is doing is it's ingesting, and this is just a single sensor example. In the next slide, we'll see a multi-sensor example. But it's ingesting this data, it's processing it, forcing it through its compressed layer, and then reconstructing it. And this is its reconstruction here at the top. And again, remember, we want the reconstruction after training to be as close as possible to the original. And here we're showing how those two things overlap. And the idea is that it's not a perfect match, and there's going to be reconstruction error, which is essentially the gaps between these two time series. And what the network is trying to do is minimize that reconstruction error. But we're going to use that reconstruction error as a proxy to outliers. Essentially, anytime that the amount of reconstruction gets really high, the network can't explain the behavior that's happening right now. And that's like a red flag that will get triggered. And we'll use the past sort of reconstruction errors from a really long time window and build statistics on the reconstruction error. So we know what the usual reconstruction error is, and we also know its variation and standard deviation. And based off of those statistics, anytime that the reconstruction error gets several standard deviations away from its normal behavior, that's when we start to really care. And that's when we start to potentially consider an opportunity to escalate to these horticulturalists.
Yeah. So in essence, to kind of summarize in a more general term, which is if I were to, as a human, to look at data, so I would look through, maybe historical data from last year or so. I've trained myself on a more compressed model, meaning that I know there's a few things that I care about when I see as an anomaly, because I can't remember all of the data. So just somehow in my head, there's this model. When I see this, there's, that's called my experience, right?
That's
so
right,
I compress my experience. And when I see that, when you put new data through me, through the model or through me, I'll look at it and go, hey, it kind of looks, it looks about normal because I see certain features. Essentially, that's what the autoencoder is doing. It's so if you look at the middle layer where you have the bottleneck, that's where it's really summarizing and saying, hey, those are the most important features that I look at.
So for in this example, I'm seeing a little bit of maybe early afternoon traffic and a little bit of late afternoon
normal.
like cloudiness or something like that. So it's having to figure out a condensed representation of an entire day. And then from that condensed representation, be able to re-explain everything back against the original dimensionality. And so, we've been sort of hoping to give you guys a little bit of an intuition about how these architectures work. To take this a slight level farther, and we promise this is the most we'll get involved in modeling deep learning for you today, this being an architectural talk. But here is just a demonstration of how you go from single sensor autoencoders to multi-sensor autoencoders, and that's in fact what we're working with. And essentially all you do, and it's not very complicated, is you just take the sensor streams and you sort of append them to each other or concatenate them and make one really long input to the architecture. And then on the other side, you expect the reconstruction to sort of map to those same coordinates.
Exactly. So in here, we can show this as an example. So if there are, let's just say, 10 different sensors coming in, so your input would essentially be, let's say, 96 data points from the same sensor. So our sensors fire off every 15 minutes. We multiply that by 24. That's 96.
Per day.
So that would be
the first 96 values.
First 96 cells as input. And then the next sensor,
from one sensor.
Then you append the next sensor, which is also 96 sensors.
That's right.
So we end up having about 2,400
or
so
sensors per zone.
Sensors per zone.
And we're getting to the zones here in a second.
That's right.
But this is just exactly. So we just append the sensors to each other, and that same mapping is retained on the output side. And so when you look inside the spheres, there's these tons and tons of sensors. How can we actually, break them up into some reasonable, understandable format? So essentially, the approach that we took is to look at different zones of the biospheres. And so we were working with some of the building automation guys, and they were kind enough to share blueprints that show us both, the different regions as well as all of the different sensors that live there. So we now finally had a mapping of all the data streams we were reading to actually something that's physically grounded in the building.
So we end up having 4?
So we chose four zones, and we'll show them in here in a second, but this is how it sort of came about. There's many possible ways to slice and dice this, but I think the 4 that we chose are sort of vetted by the horticulturalists, so that's a meaningful thing. And just to speak briefly about the sensors that are in here. So for example, if we look at just the the North Conservatory, which is this region on the first floor in this outermost shell, I guess.
Yeah.
You notice that there are these AC sensors, and there's 4 of them in the North Conservatory. And if you were to try to find them physically in the building, you would have to sort of look really carefully because they're kind of hidden amongst the foliage and the tree bark. And here what you see is this little wire mesh with a tube attached to it. And the tube is actually pulling in air all the way down to the basement of the building, where there's this air acuity sensor that actually looks at all of the air coming through and is able to pull out CO2 levels, dew point temperature, relative humidity, all of these pretty complicated chemical processes.
Yeah, essentially the sensor is concentrated in a box in a basement.
That's right.
And the way you think about it is that it's almost like having tubes that are extended to different areas of the building that sucks in the air and samples them through that system.
It's like you have an elephant trunk and it's bringing it to the brain.
That's right.
And so we also have quite a few of these instantaneous light sensors that are distributed in the building. And so those are the ones that are labeled DLI, which I haven't highlighted here, but they look something like this on the right-hand side. Yep. And so we're basically getting, I would say, 5 different types of data reliably from all these zones: CO2, relative humidity, dew point temperature, and instantaneous light. Yep. And so here, if now that have kind of had a chance to think through some of this stuff and met again with the caretakers, we decided to chop things up into these following zones. So there's in blue here is the North Conservatory, the one we just talked about. On the other hand side, on the next floor, is the South Conservatory. And then running along all 4 levels of the building is the living wall, which is shown here in green. And so these are actually the blueprints of all the different floors going from left to right, 1, 2, 3, 4. And then the 4th zone is this canopy, which sort of is on the right-hand side, and it stretches over 3 floors, and it captures this really large tree that's sort of one of the centerpieces of the building.
It's a ficus tree.
That's right. That's right.
It's really big,
Yeah.
And we actually ran into some problems with insects, and we can talk about in our future work where we're going to use spectrometers.
That's right.
Okay.
Yeah. So anyways, now that we sort of selected these zones as meaningful ways to potentially target anomaly detection, this will help with the interpretability problem, because now what we end up doing is we end up having models that are trained by sensor type within each of these zones, so that if you get an alert, hopefully very rarely, as the caretaker, you would know where it's located, and you would know what type of sensor is causing it. Yeah. So that's kind of the motivation behind this sort of geographical splitting of the model building.
So a lot of times, if you look at building machine learning models, the first thing is we always do is to really go talk to the customers and really figure out what is the business problem, what kind of problems they have, and what do we actually have in terms of the sensors that, IoT is largely based on the kind of sensors we have.
Absolutely.
And whether we need to get additional ones.
That's right. That's right. And it turns out actually that there's a bunch more sensors in here that aren't hooked up to the system, but hopefully because of this project we can get them hooked up.
Exactly.
Okay, so let's see. So let's talk a little bit about the actual sort of computational and systems architecture that's happening behind the scenes. So I guess everything is happening these days with Lambda triggers that are being periodically scheduled. Do you want to talk about that a little bit?
Yeah, sure. So essentially the building already has a system that collects the sensor data. It's stored somewhere, but it does provide us with an API. So there's an REST API. So we use a Lambda to actually retrieve the data from that system. I think it's once a day, or is it once a day? Or once an hour?
Once a night. Once a night.
Once a night, we essentially pull that data into a S3 bucket. And then we essentially just rename them.
Right. So the Lambda function wakes up a P3 EC2 instance. And then the EC2 instance goes through and does all of this work. When we're developing these ML models, we're using SageMaker and Jupyter notebooks, which we'll demo here in a little bit. But once it's actually time to sort of deploy, you strip the code out from the notebook, you make it into a Python file, you put it in a P3 instance, and you have the Lambda wake it up periodically to do batch processing.
That's right. There's different ways you can host the actual the inference, which is how you actually build a model, how you actually run through the model to look at there's an anomaly. SageMaker itself has a hosting endpoint service.
That's right.
But and it provides you with different type of instances. And we can also talk about some of the newer elastic inference stuff we
That's
just
right.
put
That's right.
out.
Yeah, no,
today,
this is still fairly early days
Yeah.
with this project, and the final chapter hasn't been written, neither on the research side nor on the sort of architectural implementation side. So we're just trying to put all of the building blocks together in a meaningful way, but then how we choose to execute them ultimately will depend on what the folks who are serving.
It may change,
Yeah.
and it also depends on a lot of different things, right? For example, the cost, the size of the model,
Right.
And also the convenience, how much time you actually have to.
That's right. That's right.
And who would be maintaining the system?
Exactly. Yeah.
And also how often the model need to be updated, not just retrained, but also
Right.
updated. If there's like new sensors coming online,
Right.
and also the level of expertise that people have. So ultimately, your
That's right.
architecture is dependent on that. But here is actually a
Let's
reference.
Let's really quickly talk through the steps that
Yeah.
sort of the data takes as it's being processed for training. So, as Wei-Ming was saying, we currently are using for training. Actually, we do the training once every week. And currently, the way it works is we query the entire year of 2018 to date in a single query, and we use that query to, first of all, we use it for numerous things, but we need to pre-process it. So we resample everything to 15-minute intervals. We compute scaling statistics on every sensor category. We focus only on the weekdays, and we sort of trim and extend the sliding windows to make them all fit the sort of.
If there's a missing value to it.
That's right.
So, one thing I want to also emphasize is in the machine learning and in the process, the first part is understanding the business problem. The second part is really data selection. The data selection and cleaning up the data took, I would say, usually 90% of the time. So in this case, it's probably more like 80% of the time. And then you would actually go build the models themselves. So in this case, the data itself is relatively clean because they are relatively, I would say.
Yeah, the data is clean, but it's more about figuring out how to normalize it, how to properly scale things, how to fix the missing samples. The fact that we needed to look at weekdays separately, just all of the data exploration and data wrangling is totally the majority of a data scientist's work, right?
Exactly.
And so then once we have gone through this entire process of pre-processing this data, and this is, by the way, happening for each zone, right? Each of the zones we described. So there's four zones, four zones. And each zone is going to have 5 models inside of it for a total of 20 models total. Yeah. And so, you query all the sensors in a zone, you process all of the sensors in a zone, then you build models, up to 5 models, one for CO2, one for temperature, one for dew point, one for relative humidity, one for instantaneous light. And for each of those sensors, you're essentially setting some parameters, but ultimately, these things are not too critical. We can talk about them offline potentially. If folks are curious, please ping us. But you need to define the characteristics of the network that you're building, and ultimately, this network does around 50 epochs of training of passing through this entire data set as it's tuning itself. And then finally, when the model is trained, it saves itself and converts it to this intermediary representation, this ONNX format.
Open Neural Exchange format.
That's right, Open Neural Exchange, which can be consumed by pretty much any deep learning framework. And in our case, ultimately, it ends up being consumed by MXNet. And so here, we end up doing an evaluation stage where we take the trained model that we just built on all of this data for the past year, and now we ask it to go through and produce its predictions and look at the reconstruction error for the entire year. And using that reconstruction error, we can come up with statistics about it. So we figure out the mean and the standard deviation of the reconstruction error. And that's going to be critical for us in order to be able to figure out when things are happening that are really unexplainable.
Yeah, essentially you're using that to set the actual thresholds when it comes to standard deviation after the reconstruction error.
That's right. It's kind of like figuring out what the tolerable amount of surprising stuff is, so that you can figure out when anomalies are happening.
In that particular phase, we usually involve the domain specialist. In this case, it's going to be Ben and Claire. They're going to tell us, hey, we think this is an that was. So using that knowledge. So in essence, this is semi-supervised learning.
It eventually ends up there, right. Yeah, and so once all of this, goodness is all done, everything gets stored in S3 in sort of a zip representation, and each zip has all of these things that we computed along the way: the trained model parameters, the time sequence for which it was queried, the scaling statistics for each sensor group, the neural network architecture, and so on and so forth. And this essentially is, again, running on a P3 instance these days with, we're actually parallelizing the training part. So each GPU is training one zone.
It's a task parallelism rather than...
That's right, that's right. Did you have anything to add?
Yeah, so actually we want to talk more about the new announcement we just made.
Sure.
We have a P3DN, and the P3 is the Nvidia Volta processor, which is capable of doing 120 teraflops worth of computing. That is a lot more. That's hundreds of times more powerful than a regular CPU when it comes to this type of workload. And also for the 8X, you're really looking at having 8 GPUs in a box. With NVLink connected very fast interconnect. So our new announcement is really the DN, P3DN, which stands for doubling the amount of memory than the original P3 instances.
That's right.
Now it has 32 gig, and also has much faster networking.
That's right,
which is
100
at
gig.
100 gigs.
Right, right.
So for a lot of people, this would be very helpful because
Yeah,
you're
that's
trying to...
amazing. Yeah, you can do multi-node training.
You
now,
have a very fast, powerful processor, but you certainly also want that data pipeline to be wide so that you can point the data to the training.
Absolutely. And actually, Nvidia just announced our Rapids product, which is meant to accelerate, GPU accelerate all of sort of traditional scikit-learn and pandas style data processing. So that the new instances are going to be perfect for it. All right, so let's talk a little bit about what happens now that we have trained the model. The next thing that happens is essentially the inference architecture. And there's many ways you could deploy this. You could deploy this in sort of a real-time way where you could run inference every 15 minutes when a new sample comes in. Or you could do it the way we've been doing it, which is to do daily batches at midnight. And so essentially here, we pull in the trained model, which is this zip file that's got all of the stuff that we previously computed. And again, for each zone, we go through and we do the same thing. We just do the pre-processing steps, except now we're not computing the scale statistics, but rather we're applying them from the pre-computed values. And here we're now just looking at this. Once this data is pre-processed, we can just send it through the model and see what its reconstructions are. And we're comparing those reconstruction statistics to the ones that we've looked at when we built up our really long query over the span of a year. Anytime that the reconstruction is in what we consider to be the yellow or red region, which is more than 3 standard deviations away from the mean, and then more than 6 standard deviations away from the mean, that's when we start to consider potentially escalating to a human.
That's right. And at the end of the day, the most important is whether that particular signal is actionable.
That's right. That's right. And so that's why we're very conservative with what we consider to be the red here, which is 6 standard deviations away, which is...
That's 99.9.
No, that's a lot of nines.
Yeah, lots of nines in there. One of the other things I want to point out here is the inference architecture we're talking about here. Inference actually just means that once you have the model trained, you're doing the prediction, or you're doing the classification, the scoring of whether there's an anomaly. In this particular case, you're really scoring. You end up having just a number that we'll look at, whether that's out of the standard deviation. So the inference can be done on hosted using, like I said, SageMaker has a hosting option which you can just simply use. It can stand up a CPU instances or GPU instances. So for what we are doing here, a CPU is probably sufficient. But when it comes to images, you might have to consider having a GPU-like instance. So today we actually announced elastic inference EC2 instances. So the idea is that you can rent a fraction of a GPU. So if you're not going to use the 125 teraflops worth of power to constantly doing these kind of predictions, you could actually rent a smaller one. So the smallest instance is 8.
I think it's 1 teraflop.
1 teraflop, 32 bit,
yeah.
So it's probably 1/16 of
the cost
of the size of a regular GPU.
Right.
So essentially, you rent a smaller piece, and then if your inference is not a heavy load, you could essentially paying just 10-20 cents for these things, rather than paying for the full unit, which is $3, I think.
That's
three,
right.
three or
That's
$4.
right. Yeah. So elastic inference
Yeah.
would be a great architecture to use.
Exactly.
With this. Once you've trained your models and
Yeah.
now you're streaming small pieces of data through, it's a good thing to use for that.
Another thing about inference is that it's very scalable horizontally as well. So let's just say I have 20 models. So each of them, I could host, multiple models on one instance.
Yes.
I could also host them across. Let's just say I could run 20 of these P3s that have really heavy workload.
Right.
And if I want to scale up even further, I could. Essentially, they're more or less very horizontally scalable.
Oh yeah, absolutely, absolutely.
For inferences.
That's right.
And also, I want to emphasize the fact that the majority of the cost. A lot of times, people think about the cost of doing machine learning and deep learning is the training. It's actually not quite true, because when you do the training, it takes about maybe a few minutes to a couple of hours. Maybe the longest training for our recent project, which is the shoe game project, it took about 2 days and 5 hours, and that's
that's a rare.
Yeah, that's
exception.
rare, right?
Yeah.
So you would never go over just a few hours. But if you, let's just say you have a website, or if you have these really large IoT projects where you have millions of sensors, you could potentially save a lot of money by building the right inference architecture, and also being able to just scale without having to think
Absolutely.
about it.
Yeah, and as we talk about here towards the end, there's also comes a time when you may want to sort of graduate to on the edge devices that are doing the processing there, so that you don't have to be constantly sending data around. And especially once you start dealing with
Images,
things like cameras,
That's right.
yeah, it makes a lot of sense to do it on-prem. And we'll get to that in just a second.
Sure.
Just to sort of close the loop here, up till now, everything has been in the domain of unsupervised learning, and that just basically means that you're not there's no human supervision up to this point. But at the very end of this process, whenever an escalation occurs, whenever we think that something surprising or potentially anomalous has happened, it gets sent up to our caretakers, to the horticulturalists, and typically this is only for instances of things that are in the the red domain. And they're asked to assign a label, like, was this an anomaly, yes or no? Things just get sort of added to a backlog for them, so they don't have to do it in real time. And then in addition to that, they can assign an outcome to it, like what kind of an anomaly was it? And this is things that we're going to take and try to build anomaly classifiers, so that when anomalies get popped up from this architecture, this sort of unsupervised architecture, they'll get propagated to a supervised model that will be able to say, okay, I think this is an anomaly, yes, and then what specific type of anomaly do I think it is?
Yeah, essentially it's cascading that.
Right. Hopefully lead to more actionable stuff and interpretability. Yeah.
That's right.
Okay, and so let's try to, we've only got 11 minutes here, so let's try to move quickly. This is just, for folks who are curious about how you might be able to trigger something similar, this is how you sort of would design a Lambda function to wake up your EC2 instance, for example, in this very simple example.
You're just spinning up it every night and turn it off.
That's right.
And you can certainly use an API to call the SageMaker training API directly, but it has to be one of the algorithms. But let's just say our stuff is like custom.
Right.
One of the easiest ways to do it is to just spin up an EC2 instance. So in here, the way it works is that you create a Lambda function, and then you create an event in the CloudWatch.
Event source,
event source. So inside CloudWatch, you can select a scheduled event. And then you send it to the target Lambda function, and then you suddenly have a very simple kind of a cron job like system. And then when you want to shut it down, you can have send it a message to a Lambda function and shut it down.
Yep. Awesome. All right, so let's just really quickly do a very brief demo of the notebook that we built to show you guys some of this stuff. So let's start maybe just by regenerating this figure so you guys can see that this is actually a live session here. And again, this is just our correlation matrix that's showing the weekday versus weekend behaviors. But let's do something more interesting. So here we're going to actually train a model on the fly. And actually, before I do that, let me show you just a couple of days of behavior, just so you can get a feel for it, what it looks like when it's all been sort of flattened out. So this is what our samples look like that are being fed into the architecture. And the first 4 of these are the CO2 sensor values. So in blue is 1 day's worth, then in orange is the next day, and then green is the third day. So these are 3 different days, and then there's 4 different sensors of the same type, the CO2 sensors that are in this I think this happens to be the South Conservatory Zone. And so after the CO2 sensors, I believe are the temperature and dew point sensors up here. And then after those are the relative humidity. Oh no, these are instantaneous light, and then relative humidity is up here. Yeah. And then we've also got some things like external conditions, like what the temperature was in Seattle. And then there's other things too, like I think this is the external humidity. Yeah. And then we have another indicator variable here that just basically shows you what hour of the day it was. Yeah. And whether or not it was, what day of the week it was.
Yeah, essentially, this is the input for the autoencoder, where you're kind of concatenating all the stuff together, and you're passing it through the neural net.
And typically, the autoencoder would only see a single one of these, and I'm just showing you 3 just so you can see the diversity over multiple days. So this is what the kind of thing that the autoencoder would be getting as input. And so now let's actually build and train a model, and you guys can actually see the training happen in real time here. Okay, and so here is the definition of our architecture. So in this particular case, we're getting in 2016 features because we've discarded some of them for the purposes of sort of throwing away things that are negatively correlated with this particular experiment. And this happens to be a CO2 targeting model. So this model is trying to learn how to look at all of the data, but then only really reconstruct the pieces that belong to the CO2 sensors. So it has a chance to learn from all of the sensors, but it's only accountable for reproducing the CO2. Right. And so its architecture is sort of ingesting 2016 samples. Then it's sort of doing a kind of a funky thing for an autoencoder. So it's starting out fairly wide, then it's going even wider to give it a chance to learn from all of these interesting relationships. And then it's sort of repeating that for one more stack, so it's wide, wide, and then original size, and then really narrow, and then reconstructed.
That's right.
So there's many variations you can play with. This is one that seems to be doing quite well.
And that's essentially the job of a data scientist, which you're actually...
And it just finished training, by the way.
Yeah, great. That's really fast. Yeah.
So let's take a look at some of its outputs here on a couple of days. Okay, so here are just randomly sampled days from the data. Yeah. And you can see that it's basically getting really good at reconstructing the CO2 sensor behavior. So in blue is the original data, and in red is the reconstruction. But
we have no anomaly here.
There's no anomaly here. But all of the other sensors were basically not accountable for in the reconstruction, but they were potentially used to build the reconstruction just for the CO2 sensors.
Right. We're including that relationship, but we're not using it. And here you're just masking it out.
That's right. And you can just see that it's actually gotten fairly good at reconstruction because there's different kinds of behaviors that are going in here, and it's able to map most of them. Yeah. So I think beyond that, these notebooks we're happy to share with folks who are interested. Yeah. But we'll sort of pause there and come back and try to wrap up, just because I know we're getting tight on time. Yeah. From a results perspective, what we just showed you sort of consistent with what we're seeing for different kinds of sensor groups. Oh, make it big.
Yeah.
So we're getting one of the only indicators that you have as a data scientist when you're working with unsupervised problems is certainly in the context of autoencoders is, are you able to get good sample reconstructions? Because if so, then that means that the autoencoder has learned something. Yeah. And when we inject anomalies into these reconstructions artificially, they also throw up really high reconstruction errors, which is good because it means it's working well. Yeah. And then they're actually starting to find things for us. Like this is one of the things they found, which was apparently, so this is something that came out of the system, and then we escalated it to Ben and asked him about it, and he said, nice catch. We altered the climate to encourage the blooming of our amorphous titanium plant. Yeah. The corpse flower, as it's also known, is accustomed to warmer temperatures and higher humidity than the normal sphere's operating parameters, which is incredible because they're already trying to sort of maintain the microclimate of Costa Rica. This plant apparently needs even more humidity and I don't know. But in any case, the system seems to be already producing some fairly interesting and fruitful results. And we look forward to improving it and working with the caretakers to help them further.
And once again, this really shows that it's the machine learning model is building trust with the caretaker, which would make your system have a much better user experience.
Exactly. You want to talk a little bit more about future work?
Yes. So we're just actually starting to work on this. So at the very beginning, we actually wanted to do having camera imaging for the living wall. What turns out to be fairly difficult is that images are just plain cameras don't necessarily reveal a lot of the interesting things that are happening with the plant. So it turned out that there are these type of multispectral imaging that can actually catch diseases of the diseases of the plant stress. It actually show different colors that it would be much more useful than the traditional, just like a GoPro.
RGB,
we actually try to use a RGB system. So another piece which I want to talk about, which is edge processing. So we talked about doing that inference or that evaluation in the cloud. But if you have an area where it's remote, let's just say we're in a greenhouse, there's no internet connectivity. For example, if you're in a desert somewhere. So
that's where I love to grow my plants. Yeah.
Okay. You would probably have to have devices or I would say hardware that's powerful enough to be able to do that type of inference, especially for images. So to give you an example, I ran image inference on object detection on a Raspberry Pi. It took about 201 seconds to interpret one frame.
This was YOLO, right?
Yeah, this was YOLO, YOLO model we did. And then we tried it on one of the more powerful machines on an ARM processor. It took, I don't know, 30 seconds or so. And then on the GPU, this is actually a TX2, which is $200 little GPU device.
Size of a credit card.
Size of a credit card. It's able to do that at 3 frames per second, which is actually it's a 0.3 second to actually do that interpretation. It just tells you that GPUs are absolutely necessary for any type of image, machine learning image processing.
That's right.
Another part which we want to talk about is that a lot of these edge devices are relatively weak in terms of power when you compare it to the machines in the cloud. So for example, I'll give you an example. This TX2 is capable of doing about 1 teraflops. Yeah, it's about.
Is it 1 teraflop?
Yeah, 1 teraflop. Okay. And then the your laptop probably have a 1060 GPU.
Right.
It's capable of about 4. I have the same laptop. And then if you look at the one we have in the cloud, the P3 has 125 teraflops.
That's it with tensor cores only.
With tensor cores, theoretical throughput, right? So it just tells you that these models have to actually, if you want to fit these models into these edge devices, there's going to be some work that's involved. So part of it is something called Tensor Rt, which is the optimization engine which Nvidia provides for you to take a model that you train. It's actually taking that graph and optimize it. The reason is because when you're doing training, you have to do forward propagation through the numbers, through the system, and then you look at the error of your model and the actual label data, and then you have to do the back propagation.
Gradients or little error corrections that need very high precision.
Exactly. So in that case, if we're doing inference, you're only actually doing just a passing through.
That's right. So inference is once the training has been done, and there's only forward passes happening, which, especially in the context of images, we're finding that you can reduce a lot of the precision, but not lose accuracy. So we can throw away, instead of having to represent like the pixel value colors as 64-bit floats, we can actually represent them as
16-bit,
as 8-bit integers, even.
That's right.
And not lose precision and accuracy.
There are even you can even go a step further by fusing the layers together, removing
layers,
some of the
and it also actually does it launches mini experiments trying to figure out what matrix multiplication kernel sizes are optimal for your problem. So it does a lot of great stuff for you behind the scenes.
So Tensor Rt does that for you. Essentially, all you have to do is we have to take the Onyx format and feed it through.
That's right.
Then it can build a very tight model that can fit in these edge devices as well as your deployment in the cloud. So definitely look at Tensor Rt.
Absolutely. Great. And so I think, if you guys have any questions, please feel free to follow up with us. Here are our emails. And thank you so much for your attendance.
Yeah, thank you very much. And we look forward to maybe another session in the future.
Yeah. Take care.